In this video, we're going to discuss isomers. And so what are isomers? When you put together a molecule, generally we have a formula something like C4H10. There's a couple ways you can put them together sometimes. I could have carbon, carbon, carbon. I got 4 carbons in a row, fill them in with hydrogen. Remember, each carbon wants 4 bonds, so hydrogen, hydrogen. This would be butane. It's 4 carbon long hydrocarbon chain. I could also do 3 carbons in a line and then fill in their 4 bonds. This is 2-methyl propane. So I have exactly the same chemical formula, but I obtain 2 completely different molecules. They will have different physical properties, boiling point, freezing point. They'll give off different energies when they burn. They'll have different optical rotations. They are different molecules. And yet they have exactly the same formula. These are constitutional isomers. Constitutional isomers are completely different connectivities. Which atoms and in which order are fundamentally different. And so we see things like this with, if you have, say, propanol. Well, you've got C3H8O. We can double check that. 3 hydrogens there, 2 here, 2 here. So 3, 4, 5, 6, 7, and an 8th. Well, other ways to have put this together would have been like this. I would have had 3 hydrogens on that carbon, 2 on that one, 3 on that one. So still 8 hydrogens, 3 carbons, and an oxygen. There was more than one way to have put this together. And these molecules are wildly different in their behaviors. Propanol, which we'll talk about naming them later, is a liquid at room temperature, where this ethyl methyl ether is a gas at room temp. And so they fundamentally change as we rearrange how they are connected. And so constitutional isomers are just all the different ways you could have put those atoms together. You have a giant bag of Legos, you can make a lot of different things. Same when you have a lot of atoms. Well, if constitutional isomers are just different molecules made out of the same atoms, there is a type of isomer that is much more difficult. That is a stereoisomer. Stereoisomers have the same connectivity, so same connections. However, where they differ is direction. An example of this might be 2-butene, or but-2ene. Well, I can have the same general connections. If we look at it, that is a carbon with 3 hydrogens. That's a carbon with 1 hydrogen double bonded to a carbon with 1 hydrogen. That goes off to a carbon with 3. I see exactly the same connection pattern in my next molecule. So for both of them, I see carbon with 3 hydrogens, single bonded to a carbon with 1 hydrogen, double bonded to a carbon with 1 hydrogen, and then single bonded to a CH3. So both of these appear to have exactly the same connections. They are not different constitutionally. They are not rearranged in any fashion. But there is a difference here. One of these is trans but-2ene, and one of these is cis but-2ene. Well, imagine if you're trying to build a table, right? It matters how you put those legs together. If you have a leg go up and connect to the tabletop, you want your other legs to go down. If you have one leg go up, connect, and some of your other legs go up, Well, that table's tipping over. That is not staying balanced. It's just going to fall over real quickly. Despite being connected in effectively the same fashion in the same locations, that directionality made an enormous difference. Stereoisomers are extremely common. These directions matter enormously, and they are extremely common in biology. Stereoisomers will come up many times later in this course, especially when we discuss sugars. However, for the moment, we'll reserve them to just cis and trans. And so the idea is how you connect makes up your constitutional, and the direction that you connect makes up your stereoisomers. Now, not everything has an isomer. If you have C3H8, there's only one way to put it together. I could put the carbon here, I could put the carbon there, but that's still just 3 in a line. I could say, hey, let's put it on that first carbon. That's still just 3 in a line. All of these, despite physically drawing them slightly different, in the end, the flat drawings still give us exactly the same connection patterns. These are all constitutional. Well, they're not even isomers. They're the same molecule. So we can draw up, down, left, and right in whichever direction we want for single bonds. Double bonds, however, do produce a directionality component. These two molecules, so very close for most of it, are fundamentally different. That methyl at the end, one went up and one went down, and that changes an enormous amount about its behavior. And so for both of these is a hex 2,4 diene. For one of them, though, well, it's going to be trans, and one of them it's going to be trans and cis. These molecules will behave fundamentally different inside the body or inside any reaction system. And this is the idea of isomers. We'll explore it in more depth as we get into more biological molecules and stereochemistry in terms of the carbohydrates. For now, though, this is the basics of constitutional and stereoisomers.